Awesome. Good to see everyone. Been a while. Seems like a long time. So welcome back. So today we are going to talk and begin a different proof technique called proof by contrapositive. So that is basically section 5.1 of the reading materials if you're hopefully following along with that. So before we get started, as people are settling in, are there any questions? General questions? Just a couple of reminders. There is no homework that is due next week, no written homework. You'll have your quizzes on Monday and Wednesday, but since we only have one class today, it doesn't really make sense to force a homework assignment on you due on Monday. So there's a homework assignment open. It's not due this Monday, it's due the following Monday. I think that's like September 21st. It's longer because you have more time to work on it. So just keep that in mind. It is longer, so you don't want to hold off on it. After today, you should be able to do a good portion of it. So definitely get started on that. Okay, so just to kind of review some of the stuff that you looked at for the quiz, we are going to work with proving conditional statements today, if then, or perhaps if and only if statements. So the first thing is to recognize if we have a statement like if P then Q, the contrapositive is defined as if not Q then not P. So we flip the hypothesis and the conclusion and negate both of them. And this is easy to confuse language-wise with the converse. The converse just interchanges the hypothesis and the conclusion. So you had an example for, if we kind of stick with this example, if you eat all of your vegetables, then you can have dessert. The contrapositive of this would say, we would take Q, which is you can have dessert, and we negate it. So it would basically be, you cannot have dessert. If you cannot have dessert, then you did not eat all of your vegetables. And logically speaking, these two statements are equivalent to each other. So saying, if you eat your vegetables, you can have dessert is logically equivalent to saying that if you may not eat your dessert, that would imply that you didn't have your vegetables. Whereas the converse is not logically equivalent in this case. So there's a truth table to kind of verify the logical equivalence and not of some of these statements. Any questions about that? Okay, so then the main takeaway from this, if we're comfortable knowing how to find the contrapositive of a statement, and with the fact that if P then Q is logically equivalent to its contrapositive, then that means if we want to prove a conditional statement like if P then Q, we have an alternative, which is we can prove the contrapositive. And I'll just say sometimes, most of the time, direct proof is easier and a little more elegant, but there are occasions where direct proof is a little awkward and proof by contrapositive might be a little more convenient. So how proof by contrapositive works is we're basically going to do direct proof on the contrapositive. So we're going to start by supposing that not Q, and we want to get to the point where we can therefore show not P is true. So some helpful steps to get you going if you're having a hard time thinking like, where can I get started on some of these problems? It would be identifying what P and Q are, and then identifying what not P and not Q are. Okay, any questions? So the example that was in the video, I just want to give a quick rundown of this again, just to give you a chance to ask anything. So if we wanted to prove the statement, if x squared minus 6x plus 5 is even, that means then x is odd. First thing would be to identify that, okay, P is the thing that comes first. So statement P is x squared minus 6x plus 5 is even. Statement Q would be that x is odd. So then we can negate each of these. So the negation of Q is x is even. The negation of P is x squared minus 6s plus 5 is odd. And then what we want to do is prove if this, then that. So we start by supposing not Q is true. That's going to be the first step always when we're proving by contrapositive, is we suppose not Q. So in this case, we suppose that x is even. So then that means that it can be written as 2 times an integer. And this is a little bit nicer, I think, because it's a little bit easier to take something that we have assumed about x and plug it into this quadratic expression and simplify. So I can now replace each of these x's with our assumption that x is even. So it's 2 times a. And hopefully you're picking up that, you know, these sorts of things are pretty common in these problems where we then just rearrange things to show that the quadratic expression can be written as 2 times some integer plus 1. So that proves that P therefore is odd, right? So now we've proved the negation of the original statement P. So what we have shown is that if x is even, then this thing is odd. So now we can therefore claim that if this thing is even, then we know that x must be odd, right? Which was the original statement that we wanted to prove. Since if x is even, then we know that this thing would have to be odd. And so if this thing is even, then we know that x can't be even and it has to be odd. So that's the logical equivalence between those two. And just to kind of compare this to what the direct proof would look like, the direct proof would say, let's suppose that P is true, which is, let's suppose this quadratic thing is even. Well, then that would tell me that this quadratic is 2 times some number. And we're hoping to show that that implies that x is odd. So now if we were doing direct proof, we would need to solve for x. So it's just a little bit, the algebra is messier. You certainly could do this. You could factor or use the quadratic formula. You'd use the quadratic formula, but it's just a little bit more awkward. So it's a lot easier to know what x is and plug it into a quadratic thing than to know what the quadratic thing is and then try and figure out what x has to be. Okay, so that was a recap of what you guys saw in the video, but any questions about that process? So definitely keep this in mind. I'll just say, I know that like last time we kind of talked about like proving things is hard, and it is, and it's quite different than some of your other math classes maybe, but I don't want to scare you. I'll just tell you that like anything else, you can get really, really good at this with practice. It's just like any other skill. So if it's taking a little bit longer to get going in this class, it's not a race. It doesn't mean you're not going to be able to get this. Sometimes things take a little bit longer. But I think what's really helpful sometimes is when you look at a problem and you just have no idea where to get started, that can get really frustrating. So I do try and just put some pointers here about, okay, if you're having trouble getting started, this might be a good place to start. Okay, so these are some of the things that I would like us to work on today in groups. So the idea here is we want to solve these using proof by contrapositive. Okay, so not using direct proof. You certainly can practice direct proof, but the goal here is to use this different proof technique. So what I'd like us to start with is doing these three. And let me just take a start with number 2, because number 2 is a little bit different, because that's doing an if and only if statement. But let me copy this one. And just come to some empty space. Okay, that didn't work. So let's see, what was 2 was x is even if and only if x squared is even. Okay. Yeah, that's what we were trying to show in 2. So we've got kind of 2 statements here. Right, we've got statement P and statement Q. And just remember that when you're proving an if and only if, then there's 2 things that we need to show. We need to show that if P, then Q is true. And we also need to show if Q, then P is true. So let's start first by proving P implies Q. And this one I'm going to do by direct proof. We can walk through this one together. And then in your groups, I'm going to ask you to prove the other direction using contrapositive. But if I'm proving P implies Q, then I'm going to suppose that P is true, and hopefully get to the point where we can verify that Q is true. So anybody have a suggestion what we can do?
You can suppose that x is equal to, if you suppose x is even, then x is equal to 2a for some integer a.
Yep. So hopefully you are starting to pick on some patterns that come up in a lot of these, right? So if x is even, then x is equal to 2a for some integer a. Okay, then what makes sense to do next?
Then 2a would be equal to 2b squared for some integer b.
Yes, yeah, I think you meant x squared. Yeah, that's right. That's right. So that's true. Then x squared would be x, which is 2 times some integer squared, which gives us 4a squared, which we can write as 2a squared. And since we've written that as 2 times an integer, we know that x squared is even. So that's our proof, right? So after we say that statement, we can therefore say x squared is even. Any questions about that? So among other things, then, what the part of this problem that I'd like you to do is prove this using the contrapositive. So instead, we'll prove that Q implies P using this contrapositive approach. So in this case, flipping the hypothesis and the conclusion means not P implies not Q. So sometimes it might be helpful for you to just kind of write what the first line, what the last line of the proof might be. So if we're proving this by contrapositive, then what would our start for this proof be?
Suppose X is odd.
Yeah, so we're going to take this statement P and negate it, and that's going to be our start. So P was X is even, so the negation of P would be suppose X is odd. And then ultimately what we want to get is therefore X squared is odd. And that would, by contrapositive, show that Q implies P. So this is the part that I'd like you to fill in with your groups. It should follow pretty similarly to the direct proof that we did for the first part. Any questions? Okay, so again, once we split you up into groups, the parts that I'd like you to think about are question 1, the remaining piece of question 2 that we haven't done, and question 3. And then we can come back and share our results for that. And just kind of a reminder about this notation with these vertical bars. That vertical bar means that A divides B. So when we see something like this, it tells us that there is some integer so that B can equal A times the integer. And when we put this little slash through that line, that means that A does not divide B. But if you're proving this by contrapositive, then really what you're going to be doing is like suppose A divides B and going from there. Questions? Okay, so I'm going to break you up into some groups. And I'm going to assign different groups, maybe different ones to focus on. So, all right, so really nice job, I think, checking in with the groups with this. So let's kind of just touch base on them. I'm not sure if all of the groups have had a chance to go through all 3 of these, but we'll see. So maybe let's just start with the second one since we started this one together. So one of the problems was to prove if X is even if and only if X squared is even. This is a nice result that's going to pop up quite a bit this semester. So because it's a if and only if statement, then we need to prove both PQ and QP. So we did the first part, and what was left was to prove if Q, then P by contrapositive. So that means if not P, then not Q. So this proof would start by saying, okay, if I want to prove this, let me suppose the negation of the conclusion here, which would be suppose X is odd. And let's see. So Giselle, Heidi, Molly, you guys want to take me through what you said about this proof?
I can go.
I'll go. Oh, you can go if you want to, dude.
Do you want to do it?
Why not? I'll go for it.
Okay.
All right, Molly. Oh, no, sorry. Wait, whomever wants to do it. Sorry, I didn't mean to get involved in the fight. You seem to be outlined, Molly, so you're on, I suppose.
So then we said by the contrapositive, we said, well, suppose X is odd.
Mm-hmm.
So then we assume that x is equals 2a plus 1 for an integer a.
Okay, then we know x is equal to 2a plus 1.
Yeah, so
Or-
then
Yep.
x squared equals 2a plus 1 squared, which then we would we factor that, we multiply that out to get 4a squared plus 4a plus 1. And then we factored a 2 out of that and said 2 times the quantity 2a squared plus 2a plus 1.
Okay, so we have x squared is equal to, you mind just saying that again? 2.
2 times the quantity 2a squared
Mhm.
plus 2a. And then add 1, end parenthesis, and then add 1. And then period after that. And then since 2a squared plus 2a is an integer, then x squared is odd because of that 1. Because we just proved the x is an odd number. So therefore x is odd, and by contrapositive, that means the original statement is true.
Yep, so that's right. So we just got that x squared is odd. That's right. So and so some people were asking, do we need to say something like, should we summarize what we just did? So for example, do we need to say by contrapositive proof, therefore the contrapositive, which is if x squared is even, then we know that x is also even, which is exactly Q implies P. And so this last sentence, I would say, like in general, when you're talking to an audience who is very well versed in writing proofs, you don't have to say this. I would say right now you're writing proofs really for your classmates. And so I think for all of you at this stage, it is definitely helpful just to make this note at the end, as well as when you're reading your notes a couple of weeks from now, it's useful to put this in here. So in case you forgot what you were doing, you can just see a note that, okay, I was doing this by contrapositive. So I don't think it hurts. It's not required, but I think it's nice to include. Any questions? Thank you, Molly, very much. Thank you. Okay. If there aren't any comments, then let's take a look at the first one, which is if 3x plus 2 is even, then x is even. Okay. So we're going to prove this by contrapositive. So does one of the groups want to take control of things and just narrate through how you did this one?
I can do it.
Okay, thank you, Stephanie.
So for proof by contrapositive, then P becomes X is odd and Q becomes 3X plus 2 is odd.
Yeah, so let me just, you're right. So yeah, so really what you're saying is you're doing this, yes.
Right.
So in this case, just to kind of make sure we've got the right P's and Q's, technically like P would be this, the original hypothesis. And we would call Q the original conclusion. So not P is 3x squared plus 2 is odd. not Q is X is odd. And so I think you were saying like this is the hypothesis and then not P is the conclusion. Yeah.
Yes.
Okay, so yeah, this stuff you don't necessarily need to show. You might want to just map this out if you haven't stuck getting going. Okay, sorry, Stephanie. So back to you.
So suppose X is odd, then X equals 2A plus 1 for some integer A.
Okay.
Then 3x plus 2 equals 3 times the quantity 2a plus 1 plus 2. Or excuse me, plus 1. No, plus 2. Which then equals 6a plus 3 plus 2. Which then you can make it 6a plus 4 plus 1. And then pull the 2 out, so you have 2 times the quantity 3a plus 2 plus 1.
So 3x plus squared was equal to 2 times
3a plus 2.
3a plus 2.
And then end parentheses plus 1. Where 3a plus 2 is an integer.
Okay.
So therefore 3x plus 2 is odd.
Yep. So right, since 3x plus 2 is equal to, yeah, I think you're totally safe saying what you just did. But right, since we just wrote this as 2b plus 1, therefore 3x plus 2 is odd.
And then for my conclusion, I just said that we've shown that if x is odd, then 3x plus 2 is odd, and therefore if 3x plus 2 is even, then x must be even.
Yep, that's nice. Mind saying that again? Sorry.
Oh, sorry.
Yeah.
We've shown that if x is odd, then 3x plus 2 is odd. And therefore
3x plus 2 is odd.
And therefore, if 3x plus 2 is even, x must be even.
Okay, good. And that's a nice kind of explanation of contrapositive without actually saying that, which is nice. Yeah. Any questions from class about that?
I have a quick question on the last one.
Yeah.
So you said that okay, hold on, I can gather my
Sure.
okay. Actually, never mind. I think I figured it out again. Wait. I'm confused by the contrapositive proof part where we like explained it on the last one because we said therefore if x squared is even then x is even. How did we get, because we're proving that if x is odd then x squared is odd. So when the if x squared is even then x is even. I think I'm just confusing myself because of that we didn't finish it because then it would prove that
So we
both
proved
ways.
I'm
I'm just confusing myself.
Yeah, so we proved by first direct proof that if x is even, then x squared is even. But this wasn't.
Yeah, and that was
So then we also need to show if x squared is even.
exactly.
Even.
Exactly. Okay, we just didn't finish with that like last part to connect it. I was still trying to prove that x is even, or like in my mind, P was that X is even and Q is that X squared is even. So I was confused how that was all switched around, but it was because we were doing the contrapositive for the last part. My bad, sorry.
Okay, no problem. Okay, anything else? Okay, then the last one was if a squared does not divide b squared, then a does not divide b. Okay, and here we are assuming that a and b are integers. Okay, so there's one of the groups who started with this one. Want to share how they went through this proof by contrapositive?
I guess I'll go
Sure, I
ahead.
can.
Or we both can. I'm not even sure that we finished it. But we did identify P as a squared does not divide b squared.
Mhm.
And Q is a does not divide b.
Mhm.
And we were going to prove not Q, which is a divides b, then not P, a squared divides b squared.
Okay, good.
And I think we were going to suppose that a divides b. There's then some integer k where b is equal to ak.
Yeah, and I think what's important to maybe stop and think about as you're doing all of these is that, first of all, you've got a new method to do proof. So you're always welcome to use whatever method you like, unless you're told do this by contrapositive, which was the instructions here. But I think it's important to kind of look at this and think about, well, why would contrapositive be better than direct proof? So I would say, like, my suggestion is normally you try and start with direct proof. And if you get stuck or you seem that this looks really awkward, then you might want to try contrapositive. But direct proof is better proof. But if we were proving this directly, that means we start by assuming this. And that's a mess, right? That means that b squared, there is no integer, so that b squared is equal to a squared k. And it gets a little awkward. So we'll see that this, by proving it this way, you might see that it's a little bit more clean and efficient. But let's see. So sorry. Was it Brandon? Were you taking us through this? I don't remember who was talking.
That was me, John, but he
Oh.
can take it from here.
No, sorry. This is the beauty of Zoom, right? I don't know who's talking all of the time. Go ahead, John, if you want to keep going.
Okay, but then we just had some integer k where b equals ak.
Okay, then there is an integer. Okay.
And then I guess we further suppose that if a squared divided b squared, then there was also some integer where b squared equaled ak squared.
Okay, so sorry, I was just writing this. So, okay, we've got, if a divides b, then there's some integer so that b is equal to a times k. Great. Okay, so then what was next? Sorry?
Well, then if a squared divided b squared, then there was some integer where b squared equal ak squared.
Let me just leave this here and ask, what do you guys think about that? So kind of what's the problem with this next sentence?
We're assuming instead of proving.
Yeah, we don't know that a squared divides b squared, right? That's what we're trying to show. So we can't assume that this is true. So we start here, and then we're trying to show that that is true. So we're not allowed to claim this yet that's what we're trying to show. But this is really common to happen. So I just want to kind of mention that you want to be really careful about assuming the thing that you're hoping to prove. So this is a great start. So we've got that b is equal to a times an integer. So what do you think we can do with that in order to show that a squared is a divisor of b squared?
We can square it.
Yeah, so we can take this and you can say, okay, well, squaring both sides gives b squared is equal to a squared times k squared. So we're allowed to do that. If two things are equal, then when we square them, their squares should be equal. Okay. Great. That's good suggestion. And so now what can we say?
Are we dividing by a squared again? So we get b squared over a squared equals k squared?
So we're hoping, so when we're doing contrapositive, right, we're starting with this and we're hoping to show that. So I don't need to solve for a squared here. I want to show that a squared is a divisor of b squared.
I don't know if we just jumped to conclusions, but I basically said since k is an integer, k squared is also an integer.
Hmm?
Making b squared divisible by a squared by definition.
Yep, so that
And then-
sounds good.
I concluded it by saying therefore a squared divides b squared.
Yeah, sorry, I have that reversed. Yeah.
Contrapositive proof implying that if a squared does not divide b squared, then a does not divide b.
Yeah. So yeah. So that would do it. Any questions? Okay, so I want to back up a sec and just we'll work on the other ones on this sheet next time. So you don't need to work on them at home. We'll work on those in class on Monday. But last class we were finishing up this worksheet. This is worksheet 6, direct proofs involving sets. And we got through most of this stuff. We didn't get to this part over here in class. Some of this was on the reading quiz, but we didn't talk about it in class. So I just want to give you guys a chance to ask any questions that you might have about power sets, since power sets are a pretty abstract thing. And we can walk through a proof with power sets in a second, but obviously before we do any proof with a power set, we want to first make sure we understand what a power set is. So from the reading quiz, this was from last week. You guys did really well on the reading quiz. Power set is the set of all subsets of a set. There's a lot of sets there. And so the thing that you want to pay attention to, and that is the elements of a power set are sets. okay, which is not necessarily true in general. We've been working with plenty of sets where the elements are numbers and not sets. So if we were coming up with a power set for A, that is written over here. And the important thing is you just want to be sure that you include the empty set and you include the set itself. So every power set is going to have the empty set and the set that you started with as elements of it. So you can start by listing all of the one element sets, all of the 2 element subsets, and then we have 1 3 element subset. And if we were thinking about the power set of the empty set, that would be the set containing the empty set. And so one kind of weird thing and that is the power set of the empty set is the set containing the empty set. Okay, and so that is itself not an empty set. That is a set that contains one element. That element happens to be the empty set. So the point here is that this and that are not equal to each other, for the same reason that the number 1 and the set containing number 1 are not equal to each other. One thing is a set in that case, and the other thing is a number. So if we were trying to list the power set for this one over here, what's one element in that power set?
Would that be the empty set?
Okay, that's right. Empty set is going to be an element in every one of these power sets. Yep. What's
And then another one would be a set including the empty set.
Yep. So that would be basically saying that the set containing that is a subset. Yes.
Is the next one going to be we're just stacking set notation?
Okay. What do you mean by that?
It'll be a set containing the empty set.
That's right.
And then we're going to have a set that's basically identical to the given.
Yep.
So yeah, empty set and a set containing the empty set.
Yep. So the original set itself is a subset of itself. That would do it. So basically, we have the empty set. We have the set containing just the first element. That's this one over here. We have the set containing just the second element, which is this one over here. And then we have the set itself, which is the last one. Okay, so these are pretty abstract things that we're working with. Any questions about the notion of a power set before we try and do a proof with a power set? Okay, so let's think about question number 10 then. So here is a proof where we want to show the power set of the intersection of A and B is equal to the intersection of the power set of A and the power set of B. And so when we want to prove set equality, we want to show one is a subset of the other and vice versa, and therefore they have to be the same. So let's just pick one direction to do. So let's kind of, and I'll leave the other direction as an exercise for you to think about, but let's think about how could we prove that this is a subset of this, right? And then again, you would also need to prove the reverse of this, but we'll take this one first. So remember, to prove that one thing is a subset of another, we need to show that every element in here has to be in the intersection of the power set of A and the power set of B. So we're not changing that general process, but what is changing is what does it mean to be an element of a power set. So if you think back to how we did these proofs showing that one thing is a subset of another, these proofs started by saying, let's consider something that is in the set on the left side, right? I want to show that an element in the set on the left has to be an element in the set on the right. And I'm just going to put some things here to denote that that's a capital X now. So that's representing a set X, right? Since elements in power sets are sets. So what would it mean that X is in the power set of A intersect B?
That X is in A and X is in B.
I don't know if X is an element in A, but what are you saying? That X is?
X should be.
So if you think about these power sets over here, right? Here's an example of an element in the power set. Okay, and notice that this is not an element in the set A, right? The set A contains 1, 2, and 3. The set 1, 3 is not an element of A, but what is its relation to A?
All
It's a
of its-
subset.
Yeah,
So that's the word.
it's a subset. That's right. So what it means to be in this power set means that this set X you don't necessarily have to write all of this out, but just to kind of illustrate what's going on here, it might be nice to just indicate that this thing X is a set. It's inside the power set of A intersect B. So X has to be a subset of A intersect B. Okay, so kind of all we've done so far is just really listed out what does it mean to be an element of a power set. And what it means is not that you're an element of A intersect B, it means you're a subset of that set. Okay, so let's then think about what does this mean? Yeah, so therefore, let's say if I take some element now, lowercase x, that sits inside of set X, what do I know about this element X?
Would that mean that X must also be an element of A intersect B?
Yep.
The little x?
Yeah, so if X is in capital X, which is a subset of the intersection of these two sets, then that means every element of X is in the intersection of A and B. Okay, otherwise, if there was some element of X that was not in the intersection of A and B, this wouldn't be in the power set, right? It wouldn't be a subset. So we kind of started with, let's take some element of the power set. Okay, that element is a set itself, and every element of that set has to sit inside of the intersection of A and B. So that means it sits inside of A and it sits inside of B. So if every element of X is an element of A, what does that tell me about the relationship of capital X and A?
Capital X is a subset of A.
Yeah.
And capital X is a subset of B.
Yep. Okay, so we've got since we know that every element in X is also in A, then that by definition means X is a subset of A. And similarly, we could say, therefore, X is a subset of B. And that should do it, right? So now that we know X is a subset of A, that means X has to be in the power set of A. And if X is an element of the power set of A, and X is an element, right, that should be in X is element of the power set of A. And so now that I know that X is in the power set of A, it's in the power set of B, it's in the power set of A intersect B. Oops. So that proves one direction of this, but if we want to prove that these two sets are equal, then we need to do the opposite as well. So I think it would be good exercise at home to try and think about how could you prove that the power set of A intersect B is a subset of the power set of A intersect B. And if once you show that, then we've got that these two sets are equal to each other. So we are out of time, so I'll leave you with a cliffhanger. Just so you know, the plan for next class would be to go through the rest of these proofs, and then we're going to start thinking about proof by contradiction. So your reading quiz for Monday, I'll get that up tomorrow. That will have kind of some introduction stuff about proof by contradiction. And then we'll get into proof by contradiction on Monday and on Wednesday next week. Okay, well, nice to see everyone. Thanks for all of your work. That was really nice proving in your groups. And if you have any questions, you're welcome to stick around. Otherwise, you certainly can get started on a number of problems on the homework over the weekends. Yeah, well, that's it. Thanks, everyone.